All right, so let's start. So last time we were talking about alpha binary link decomposition of a graph. And just to recall, just to recap, one sec. Like this decomposition. So in this decomposition, you are given a graph together that have the battery. It's a graph. This is a set U and the battery. And what you want to compute is the partition of this graph, so that for each part here, the battery are well linked. So that's the, and we want each part here to be alpha battery linked, and you think of alpha as 1 over log m. That's the highest alpha we can set, and you usually think of alpha as highest possible. And then we can see that we show that just by using the canonical algorithm that just keep finding sparse cut, if you can find and recurse, you will get this decomposition such that the total of new battery edges is small. Together with the old one, they are still small. So that's the object we looked at last time, and we also saw that it gives you a way to compress the graph dramatically. That is, if you just contract each of the parts, then the contracted graph preserve all the cuts, and not just like a pairwise cut. It preserve like minimum cut between every subset of battery vertices. So, but there are some approximation of log n, right? Okay. There was some like I was a bit sloppy in the last class, but like so it turns out that I need like to have like this 4 cases of to count edges and be careful. But like the idea that I presented is just the same, but now I updated the lecture note, and you can look at the proof. The idea is just the same, but this is more formal.
Maybe quickly, I guess I was wrong last time about whether we would like to choose endpoint inside or outside.
Right. So I think we kind of like once you be careful, you need these 4 cases and
in particular here, I've checked this updated version. So if we look at the if you could go to the next page here, in the analysis. Right, so here, in order to have this EX at most C over alpha, this is related to how we choose AI and BI.
Yeah.
So here, I guess, maybe I'm still confused, but
oh, you're done.
EX plus EYX is at most C over alpha.
You mean why this is the case?
So here, I guess there's the question about whether we use EXY or EYX. That is whether we divide according to the endpoint outside or inside. And so which one should be the case?
It should be the endpoint inside. Like let's do this offline, but I think this is correct now. Yeah. Like I need to go on to the next thing. Sorry.
Sure.
Okay. So we can also talk about something stronger. That is, we want a partition such that each part is both bodily linked and expander at the same time. And just to talk easily, I want to say that U is alpha phi linked inside G if the following is true. That is, if this graph is alpha bodily linked, and at the same time, this graph is a phi expander. Okay, so this thing, like in particular, this thing just means that the bodily are well linked. The bodily of it are well linked. That is, the edges in the bodily are well linked. Oh, sorry. The bodily edges of this are alpha well linked. That is, the all-to-all demand between the bodily edges can be rounded with this congestion, something like 1 over alpha congestion. And also, when I say that this is alpha phi linked, I want to say that this graph is phi expander. So this is a bit stronger than saying that the induced subgraph is a phi expander, right? Because I kind of say that even if you add even with this battery node, they are still an expander. Why this is why this can be like a strictly stronger thing like this if there are some node here and such that the degree inside is small, like 3, but there are like a bunch of battery edges connected to this guy, then this is gonna be sparse cut, right? So this is a bit stronger than just saying that this induced subgraph is a phi expander. But yeah, I really want to say that this is a phi expander when we say this. Okay. And in particular, when this thing happens, it means that edges inside this graph together with the battery are 1 over phi well linked. Yeah. So that's what we mean. And we can also show actually that given any graph given a graph with battery and some parameter phi, you can actually find a partition such that each part is alpha phi linked. So this is like a stronger than both bodily link decomposition and expanded decomposition, right? Each part is just like both of these is certified. Okay. And alpha, you can think of it as 1 over log again. And the number of battery battery edges in total is gonna be something like the O battery edges plus phi volume. So this kind of makes sense. This part makes sense, right? Because this thing you need it from the battery link decomposition. This one you need it from expanded decomposition. So if you want both, you will need like both term. Yeah. And Actually, this can be done, and I will just skip how to do it. But the idea is quite simple. The idea is, again, like you have a graph, try to find a cut that violate alpha phi linked and recurs on both sides. And then you just need to analyze things carefully, and it works. You can get this one. So today we will see why this is useful.
Do you need both the set of edges, like the size is dou g of u plus phi volume of g? So is it tight? You definitely need.
Yeah, you will need both. Yeah, right. Yeah. So, and this is like this bound is an existential bound. If you want a fast algorithm, like you can imagine that you can get slightly worse bound by using approximation algorithm. Yeah. So from now, I will actually talk about existential result, and you can imagine that if like we have developed a lot of tools for fast algorithm, if you want fast algorithm for this, you can just sacrifice some factor, you can make it work. Okay. So we want to keep this in mind that we can get decomposition that are both parallelly linked and expanded at the same time, and not just an expander, like not just induced subgraph being expanded. Together with battery, they are expanded too. Okay. So now the next topic is gonna be like expanded hierarchy. This is like close to being close to the climax of the class now, but okay. So I want to talk about two concepts before talking about expanded hierarchy. That is a cut and flow sparsifier with respect to terminals. The first one, cut sparsifier. So when I said that you're given a graph, I said that a graph G, you given a graph G, we said that H is a cut sparsifier of G for terminal set S. If basically H preserve all cut information about S. In particular, we need to say that first of all, H need to contain S. Okay. And the next thing is that, yeah, for any subset of S, A, B, then the mean cut between A and B is preserved. The size of the mean cut between A and B is preserved in H up to factor Q. So this is an object that we have seen already from last class, right? That is like the Bartley link decomposition is a cut sparsifier. Like given the graph with battery, if you compute H by finding a alpha Bartley link decomposition of this and contract each part, then H is small now. H have size just proportion to the size of H is just proportion to the battery. But we have seen that H is a cut sparsifier of this guy for terminal set, which is the battery vertices, right? So we have seen that like one can compute a cut sparsifier that preserve all cut information about battery vertices. That's one example. Okay. There is a related notion called flow sparsifier. So when you are given G, I said that H is the flow specifier of G for terminal S if the following is true. That is, the first one is the same. You have H contain S. And the next thing is that like you want to say that for any demand, for like if you have a graph G and this is S, and let's say this is like if you have the demand such that the demand is only between vertices in S, yeah, then the congestion for routing D inside G and routing D inside H is approximately the same up to Q factor. Okay. That is inverse. Like, so recall that this is minimum congestion, minimum concurrent flow, minimum congestion for the for routing concurrent flow, for routing D in G. So in inverse, like if the demand is routable in G, then it should be routable in H. And if the demand is routable in H, then it should be routable in G, but with some small congestion. Yeah. So question about the two notion. Like, so if I said that this is a sparsifier for terminal set S, if it is cut sparsifier, it preserves all cut information about terminal set. If a flow sparsifier, it kind of preserves all flow information about the terminal set S.
Does H have more capacity than original graph G, kind of intuitively?
Intuitively, H should be smaller or H should be sparser.
Okay.
Yeah. That's why we call sparsifier. But you can always set H to be G and it will preserve.
Because you have written conversely, if D is routable in H, then D is routable in G with congestion Q in the flow, the last line. So like, so does H have more capacity than? Oh, like Q can be less than 1 as well. Q can be.
So Q you think of Q as log n or more, like so
H has more capacity than G in that sense.
So it can be like this, like H itself can be small. H itself can be small. It contains S, but it has large enough capacity so that any flow between S is routable. Any flow between S that is routable in G, it must be routable in H too. But now if you get some routable flow in H, it now can be routed in G too. But because H should be at least large enough for the flow here, so there might be some blow up when you want to route back.
Okay, I see.
Yeah. And you see, this is basically kind of the same intuition here. H should be big enough so that min cut in H is bigger than min cut in G, but min cut in H is not too big compared to min cut in G.
Right.
Yeah. And by now you should expect that they are the same kind of object, and indeed it is. Actually, like if you have a graph which is a flow sparsifier, then, oh no, sorry. If H is flow sparsifier with quality Q, then H is a cut sparsifier with quality Q too. And if H is a cut sparsifier with quality Q, then H is also a flow sparsifier, but with quality worse by a log n factor. Okay. can try to prove this, or we do it tomorrow. But yeah, I think this is now you should think that this is quite believable now, right? Since we have seen a lot of equivalent between flow and cut. Okay, but let me tell you one example like of flow sparsifier that is very simple. So roughly speaking, I want to say that flow sparsifier of expander is so simple. It's just a star. And so that's just one sentence. And now let me elaborate. So first of all, does it make sense to let the terminal set to be the whole vertex set of G? Here, like we kind of say that, okay, S, the terminal set is some small set, and we want to kind of compress graph to be of size proportion to S. So that it makes sense for sure when S is a small set. Can the terminal set be the whole thing? It can be still, like if you set terminal set to be the whole thing, for sure you cannot reduce the number of vertices, right? But what is a non-trivial thing you can do? So one thing you can ask is that, okay, the terminal set is the whole graph, the whole vertex set anyway, but you can ask, can the sparsifier now be sparse in number of edges, or has very simple structure? Yeah. And indeed, it is the case for expander. The sparsifier can be a star. So let's look at this. G is let's say that G is a phi expander, and let me define the tree T to be a star, where the leaf of this tree of this star correspond to the vertex set of our original graph. And I create, like this is my T, and I create a root, a new root, which is just a new vertex. Okay. And for each of the three edge here, for each of the three edge from original vertex U to R here, we set the capacity to be just the degree of V. Okay. Now I claim that this star is a flow sparsifier of this expander. And it's not hard to prove actually, so let's prove it. So let's look at some demand graph on terminals V, which is the whole, like just some demand between vertices in G. Okay. So what we need to prove is two directions. One is just to say that if this demand is routable in G, then it's routable in T with no congestion too. And so how to do that? Well, it's like this. Like basically, if you want to route, suppose that your demand is just from S to T, okay? And let's say that this is routable in G. How would you route it in this T? There is only one way to route. Like given any tree, actually, if you want to route from S to T, there is unique way to route the flow, right? Because in a tree, there is just one unique path from S to T. So the way to route is just to route this, like this. Okay. And you do the same for every other demand, S prime, T prime. Just send everything to the root and send it back to the graph. Okay. So you can also think like just from every node perspective, you just really send everything to the root, and then the other endpoint will match at the root, and then you complete the path, the flow path. And now there will be no congestion. Like the congestion is at most 1. And why is that? Well, you know that suppose that this demand is feasible in G, no congestion in G, then the total demand that end at S need to be what? Need to be at most degree of S, right? Because if it's more than degree, then there is no way it's feasible. So the total demand at U for every U is at most a degree. But now, what do we do in the tree here? The capacity is just the degree of each node. So this capacity is set to be large enough for sure, so that you can send flow. So you can, given the demand in G, you can route in T too. Okay. That's one direction. And now let's prove another direction. If the demand is routable in T, then I want to say that it's routable in G with small congestion. And why is that? Well, it's here. If the demand is routable in G, then this demand must be degree of G restricted, right? Just again, like every guy here can send at most, like every guy U can send flow at most this much, because you have only one edge out of U. Yeah. So the demand must be degree of G restricted. But we have seen before that in the expander, if it is a phi expander, you can route degree restricted demand, any of them, in 1 log n over phi congestion. So that's why we get very simple flow sparsifier for any expander. We get just a star. Okay. And actually from now when I said that H is a flow sparsifier of G, if I don't specify terminal, it always means the terminal set is for the whole vertex set of G. Okay. So that's one simple example. And now, let's try to apply this idea that works for expander to arbitrary graph. And as usual, the way to do this is to use expander decomposition. But we will need a paralleling version of expander decomposition too. Okay. Again, to recap, this is a decomposition where given a graph with parallel vertices, you partition U, right, such that each part is alpha phi linked, and the number of battery is small. The total number of battery is small. And throughout this lecture, you should think of alpha as 1 over m. But you should think of phi as something that is strictly less than polylog. So phi is much smaller than alpha. Okay. At the end, I will set phi to be something like this. All right. So now let's look at this, how to get a sparsifier for any graph. You have a graph G. Then let's say that I compute alpha parallelly linked phi expanded decomposition script U of the graph. So let's say this is the decomposition. Then let's say that, and now let's look at the, suppose that we contract each part ui into a vertex ui and call this contracted graph gu. So this part is gu. Okay. This part is gu. And then basically for each of the part here, we have an expander. So what we try to do is just try to use the idea we have seen before. That is, for each part ui, you attach the star rooted at ui, like this. And the capacity of this, if this is V, then the capacity is like degree of V, just like before. And do this for every part. Okay. So your graph is gonna be like some smaller graph, some smaller contracted graph GU, and then each part you have a star, like this. Okay. And now the claim is that this graph, like I call this whole thing H. Yeah. And the graph H is gonna be a flow sparsifier of G with quality something like log n over phi, or 1 log m over phi. So actually it's gonna be something like this: 1 over alpha plus 1 over phi times log n, but 1 over alpha is smaller than 1 over phi. Okay. So you see that, okay, this is not super simple yet. It's not a tree, it's not a star, but it is a bit simpler in the sense that this part of a graph is a smaller graph. It's like just a contracted graph. The size of GU here is going to be something like phi log phi volume of G, right? The size, the volume of G here. So although I use alpha Baddeley link decomposition, but like G in the beginning has no battery, so we don't pay the battery term in the size of GU. Like, because the size of GU is really like just the number of battery edges in the decomposition, right? So you have the graph which is smaller, and then for each part you attach a star. So it looks at least a bit like better than the original graph. Okay, so let's try to prove that it is a flow sparsifier. Okay. So to do that, I need one definition. Like for any demand on the terminal V, the whole vertex set, we will say that D sub U is the projection of D into the contracted graph. Okay, so that is well, when you have demand in G here, like you can define the demand in GU, where like the demand between these two parts is just a total demand between the demand between these two vertices in D sub U is just a total demand between the two parts. That's how we define D sub U. Like you can kind of contract contract the demand, basically. Okay, so now let's do one direction. Given a routable demand in G, we want to route it in H with no congestion. Okay, so actually, like the way we create a graph is kind of already quite straightforward. How should we route the demand, right? If I have the demand from X to Y in G, how should I route it in H?
I go to root.
Yeah, like this guy just go up to the highway, kind of go up. This guy too, go up, and then try to match in the contracted graph. Try to match this path in the contracted graph. Okay. And suppose you think like, suppose that everyone just send their demand up to its root. That will induce a new demand in the contracted graph. What is that demand? What is going to be the demand in the contracted graph?
du.
It's going to be du, exactly. Yeah. So basically, yeah, I just write this. Say again. Given any demand x, y between what it says, what you do, you just send from x to its root, from y to its root, and connect the root. Well, note that to send everything to the root, this use only the star edges, right? And we've seen before that, like, because we set this to be the degree, the capacity here to be the degree of the node. So there is no congestion to send everything to the root, because it was feasible in G. So the total demand at X is at most degree of X. So sending everything to the root, no congestion on the star edge. And to connect this part in the contracted graph, we use this joint set of edges. Okay. So now I just need to say that the demand, the du in GU is routable too. Right? That's the only thing we need to say, because to send everything up, we use the star edges. Now we need to use the contracted graph edge. But if D is routable in G, then du actually need to be routable in GU too. Actually, it's going to be easier to route du in GU. So I will just claim this, and you can think about it, but it makes sense. Actually, du is routable in GU if and only if du is routable in G when you even like set the edge capacity inside each part to be infinite. So when you set the capacity of everything here to be infinite, you can route everything inside the UI really freely. Everything here is infinite. So if du is routable in GU, then du, like D is going to be routable in this graph, this kind of graph where you set, like, when it's free to route inside. But D is routable in G itself, so du must be routable in GU. Okay. So yeah, so we kind of decompose so now we have seen that like we can route the demand in dash, just send everything up and mesh in the highway. Okay. So by the way, this is this is kind of the advantage of how to think about flow sparsifier instead of cut sparsifier. Because when you think about flow, you think about path. Path has like just two endpoints, and you can compose the path. So that's why sometimes it's like if you want to say that, okay, this graph is a cut sparsifier of G, although like it's weaker than flow sparsified, it's just easier to think about flow. But we didn't complete the other direction. So let's say now that the demand is routable in H. We want to say that it's also routable in G with this congestion. So now I want to just kind of decompose the demand a bit. So the demand is just like a sum of or union of a bunch of demands. So I just said that I decompose the demand into here a sum of di, where di contains all demand, where both vertices, both end is inside ui. And what is left is just the demand such that the two endpoints are different part, right? So the demand can be thing of the union of this thing, or it's just write a sum. That's kind of the same. Okay. Now let's look at each part one by one. If you have the demand di, this is just completely inside ui, then I claim that this demand is going to be routable. Like, okay. So we have di. Okay. Di is routable in H. How it is routable in H? Di is going to be route like within the star edge of H, right? How are we going to route this in G? Well, we have just seen before that if this is an expander, if this is an expander, if you route, if you have the demand in the star here, you can route also in the expander, right? And the congestion is going to be what? Like 1/5. Yeah. This is the same construction, the same argument like before. Okay. And also there are like many di for like d1, d2, d3. This is the route to route this di simultaneously. They use disjoint part of the graph, right? The routing inside di is just route inside each di. They are disjoint. So you can route every di simultaneously in G with total congestion log n/5. So we are done with one part. The other part is now about d-diff. The d-diff to route between parts. Okay. So we know that, okay, because D itself is routable in H, then there is a feasible flow for routing D-diff too, because D-diff is just smaller than D. So let F of H, Fh to be the flow that route D-diff in H, the feasible flow. Okay. And like before, no matter what this F is, it's gonna look, each flow path is gonna look like this, right? If you have the demand from X to Y, no matter what, it just need to go up to its root first. It need to go up to its root, and then it is sent here in GU. It will connect somehow in GU. There are many other like cluster, but I just draw like the guy that the flow path use. Yeah. Okay. So let me define FGU to be the flow in GU. This is obtained from FH just by restricting this flow into edges of GU. So really just remove the green edges. Then I have obtained this FGU. Okay. And observe that this FGU is route some demand in GU. What is the demand that it route? It's going to be just the projection of d diff into the contracted graph. Right? Does it make sense? So, like you have each part here, and you have the contracted graph here. If you say that, okay, look at the flow path of FH, there are like many flow paths can be like this, from X to somewhere and then go here, and then there can be other thing and other thing, like, no, sorry, this. Like when you just said that everyone below just send up what they want to send, then the demand, like if this guy want to send here and this guy want to send to here, then the demand between these two things is just going to be the projected demand, right? So I like what I do here is just look at, I have FH, and I look at the FGU, which is now just truncate the endpoint to be the endpoint in GU. Then this guy is gonna route the projected demand. Right? FH route is D diff, so FGU will route D diff U. Okay. So now what we want to do is that okay. So what is good about this flow is at least this flow, the flow in GU, this edge in GU used to be edge in the real graph, right? It's like a intercluster edge in the decomposition. So if you, like what we want to do is that, okay, you have FU here, FGU. We want to somehow put it into our original graph. So we just write it down like this. For each of the flow path, we put the flow here. But in order to get the flow in G, we need to connect this path together. Like the path here need to be connected somehow. Right? And this endpoint need to be connected at least to the guy inside. Okay. So yeah, so basically in order to connect the broken part of, like, you have FGU in H, but once you kind of put it into G, you get a lot of broken path in G. Now, to reconnect this path, this will induce a new demand. That is, like because each of these you want, like, look at each UI, right? Now you get the demand that this guy should be connected to this guy. And so if UI is like this, there are like, now you can imagine that there are many x1, y1, x2, y2, that, like, they use some path that cross, that go through UI in G, in the contracted graph. This gives you the demand in UI. Okay. So if you count this, like, if you sum up this demand, this total black demand here between battery, it's just gonna be some demand between battery edges in total in for each UI. But what is the demand here? Like note that it's gonna be like this guy wanna send maybe one unit to this guy. This guy wanna send 1 unit to this guy, and so on. Right? That's what I mean by one restricted. Why it is one actually? Why it's not like more than one? So because this thing is from FGU. And FGU is a feasible flow, right? There's no congestion. So the amount of flow that you want to send through this is at most 1. Yeah. So this is like it's a one restricted demand between battery vertices. And now if you want to route this demand, what is the condition? Given that GU is alpha battery linked. Right. It's going to be 1 over alpha and log n factor. So you can route this black demand using log n over alpha congestion inside each UI. So this is happening simultaneously for every UI. For each UI, you just route inside UI, so they are disjoint. So no congestion is like is interfering between each part. Okay, so by the way, we need to be careful because there is a green demand here too. By green demand, I mean this part. So note that this is not between battery, right? Because X is inside, Y is inside. Yeah. But to route this green demand, it's gonna be easy too, and the reason is that so you see, I claim that you can route this green demand in total, like the total green demand can be routed in 1 over 5 as well. And the reason is that this green demand here gonna induce like when you sum over a total like flow path, this green demand gonna induce this restricted demand inside each UI, right? Like first of all, like X, okay, X might want to send to many. X might want to send something to many Y, like Y2, Y3, and so on. So it's gonna be, there will be like a demand from X to something else here, to something else here. But at like the total demand from X, it's not gonna be more than degree of X, right? The total demand of X is gonna be at most degree of X, but degree of X is the same as degree of X in this graph. Okay. How about other node? Well, this other node here, actually, the total demand that it need to receive, actually gonna be, you can bound it in a slightly better way. Actually, it's gonna be at most the number of battery node incident to it, right? Because X need to like send it when X need to send something outside the cluster, you need to send it through the battery edges. So this guy like will receive at most the number of battery edges incident to it, which is at most the degree of it in original graph. Are you with me? So what I mean is, that if you look at the battery here, if you look at this guy, this node, maybe look at X. So the flow that, the demand that kind of it is at, actually, sorry, actually you don't need to think about this part. So there are, like in this graph, with battery, there are battery edges and non-battery node X here. The total demand that X wanna send for green demand like this, X gonna wanna send demand, but this in total is gonna be at most degree of X in this graph, right? This you agree, right? And each of the battery node here is gonna receive at most one, because the flow is feasible. So, and this is also at most the degree of, if you call this the guy here, is the degree of this guy inside this graph. So everyone wanna, like the demand of everyone, the green demand here induce the demand inside inside G breast UI, where everyone want to send or receive at most is degree. Okay. So you have this degree restricted demand between vertices, including the boundary guy in this graph. But this graph is an expander. Like note that like this is where I need that not just the induced subgraph is an expander, but is expander. Not just this, but I need that this is this is a phi expander. This is where I want this thing, because it's the demand between boundary edges too, boundary nodes of this guy too. But yeah, this demand is degree restricted, so you can send flow with 1/5. Right. So that's it. Like there are several parts, but for each part, the congestion is just 1/alpha or 1/5. So the total congestion is 1/alpha plus 1/5. Okay. Question?
Is the first part actually can merge with this last one? The first part is like flows within the within the same.
Actually, yes. In total, they're gonna be like it's not like 2/5. It's like in total, the total demand of first part and the green part is still degree restricted. Yeah, good point. Yeah. Okay. So to summary, given any graph G and its parallelly linked expanded decomposition, you can get a flow sparsifier by contract each part of G into GU, and you get a smaller graph. And for each part, you attach a star. Okay, so that's like already like a full flow sparsifier of quality like 1/5. 1/5. But once you see this thing, like you can simplify a lot of things. You get a star, but you have this part which is smaller. Some graph is not so simple, but it's smaller. Now the natural thing to do is to recurse, to do some recursion in this smaller graph, right? So, and we hope to simplify GU further. Okay. Oh. So the following theorem gonna be the key idea, key tool that we would do. So what do I mean by this? Like it's gonna allow us to do recursion. So it's gonna be almost the same. That is, you have a graph, you compute the decomposition, and for each part you contract again, you get GU. But instead of having GU, just say that, okay, let HU be the sparsifier of GU with some quality Q. Okay. And now you have, like, just like before, you have G, and then you get GU here. But now let's say you replace it by HU. It can be some other graph. It can look like some tree like this too. But it needs to contain these three nodes. Okay, now this is HU. And to get H, how to do that? You just, like before, just attach a star on each of these. Okay. So that's the construction for this main theorem. And the claim is that, okay, because we don't use GU, but we use HU, and with quality Q. So the quality is not 1, it's Q, it's worse. So you need to pay quality Q somehow. It's not gonna be better sparsifier for sure. But the claim is that this guy is a flow sparsifier with quality, which is Q over alpha plus 1 over 5. Okay. So it's going to be very crucial that this Q factor appears only at 1 over alpha and not 1 over 5. Okay. So that's the claim. So now, what I'm gonna do next is here. I'm gonna specify a recursive algorithm more precisely, like how exactly I'm gonna use this theorem. And this gonna indeed, like, now you're gonna see what we call expander hierarchy, which is one of the strongest object based on expander for this whole class. And once we specify the algorithm, I'm gonna let's assume the theorem, and we will construct the flow sparsifier with good quality for any graph, and then we will prove the theorem.
Could you actually tell what is Q here?
Yeah, so you think of Q as some, it's gonna be recursive, right? So Q gonna be something that is given to you, and
in this graph where we are having G and H, what is Q then? Is it the congestion?
Q. What do you mean Q? What you asked? What is Q here?
Yeah. With respect to the example of G and H.
No, I mean Q here is just some Q. Like I'm given, like, let's say that there's some black box given GU. Some guy just gave you a flow sparsifier HU with some quality Q that he doesn't say what it is.
Okay.
And now we ask, okay, if this is Q, how bad is the whole thing?
Okay, I got it.
Yeah.
So no matter what Q is, like 1 over 5 still dominates complexity, right?
So, but Q can be bigger than 1 over 5, for example.
Oh.
Yeah.
So why is crucial that the Q appears?
Yeah, we're gonna see now. Okay, we're gonna see now. Like, let me specify what exactly is a recursive algorithm first, and then we'll see why it's important. Okay, so like the recursive algorithm is here. Let's initialize the graph G0 to be the original graph. And now what we do is that we compute the decomposition and call this U0. And this is gonna give you kind of contracted graph. Yeah, like this thing. You call this G1. You contract, and you compute the decomposition again. It might give you this thing, and now you contract, and you keep doing this. Decompose, contract, until you get one node. Okay. And that's gonna happen because when you do expanded decomposition, and if you set phi to be small enough, like the number of intercluster edges is shrinking, right? So let's say that you can do this H time. So GH has one node. So And let me call TH to be just one node. That one node too is like a great specifier, which is just one node. Okay, but now we can like do this. Now we can kind of do it top down. That is, given the graph GU, GUI, and the specifier of GUI, then you can build a flow specifier of GI, right? Using this theorem. So it's what it's gonna look like. So suppose that this is GH. Okay. So now you build TH, it's just one node. Now TH1 is gonna be TH minus 1 is gonna be like something like this. T and so on, and T1 is gonna be something like this. And T0 is gonna be like this is how the structure looks like when you apply the theorem recursively. So what you get is a tree. It's just given any graph, you can build some tree in this way. Okay. So it looks great. It is a tree. It's super simple. And now we can ask, and basically this is what we call an expanded hierarchy. So because it is built by expanded decomposition recursively, and if each of the decomposition is alpha and phi linked, then we say that this guy is alpha phi expanded hierarchy. That's just the definition. Okay, it's gonna be important object, expanded hierarchy, super strong.
So this can be defined for just expanded decomposition as well, right?
Say again?
This can be defined for just expanded decomposition.
It can be defined for just expanded decomposition. It's not clear why it will be useful. So like, it turns out the power appears only when you have bodily linkness.
Okay.
Yeah. So, okay. So now so I claim that this is gonna be good specifier. But okay, let's analyze the quality of it really. Okay. So now is the time that I point out why exactly it is crucial that you get this thing Q over alpha and not just Q times this thing, which is just like Q over phi. And know that like getting something like this is quite natural thing to expect, right? So it's like you have a non-recursive version, which is this quality, the one that we proved, and we recurse on something with quality Q. So it's quite natural that you will pay Q factor more multiplicatively. But let's see why, if you get something like this, like just Q factor times the quality that we have before, is not going to be good enough. This is because by induction, like if you get like this and apply the theorem again and again, you will get that by induction Ti is going to be quality, this quality. So go back to this. The quality of TH is going to be 1. The quality of this guy TH minus 1 is going to be log m over phi. And next step is going to be log m over phi everything square, right? Because like this thing is Q and you multiply it by log m over phi. So until the end you get log m over phi to the h. Now, what is the height of this tree? You start with the volume m and you shrink it by polylog times phi. So the height is like this thing, which is at least this. But if you set, so now you can see that you get this quality log m over phi to the h. But this is just m. So it's just too bad. Yeah. By the way, and getting m is really bad actually, because you can try to check this. If you're given any graph, unit capacity graph, and you find any spanning tree of a graph, that spanning tree is already good enough. It's already a quality m sparsifier. Or if it is a unit capacity graph, then a maximum spanning tree is going to be good enough. So this is a good exercise that you can try. But the point is, it's so easy to get this quality. Okay. Now, why this is good enough? And the point is that by induction, you can actually prove that the quality of T0 is going to be this. So I will not prove it to you, but the intuition is this. So you see that the cumulative factor here is like you pay alpha factor. Like the quality loss per level is something like log m. So this is, if you expand it out, this is q times log m alpha plus log m over phi. So the thing that get multiplied per level is log m over alpha, not log m over phi. And this is much better than log m over phi when phi is like much smaller than alpha. So the point is like every time you shrink by phi factor, which is a lot, but the quality loss is not proportion to phi anymore. It's just proportion to alpha. Right? You shrink a lot, but you lost the quality according to alpha instead of phi. And if you have this, then so alpha is just log. So this is like a log m to the h, 2h something, alpha. Oh, yeah. If you set alpha to be this much, then h is gonna be something like root log m times log, and then put everything into this, you get the quality, which is this thing, which is now subpolynomial. It's not polylog, but it's a subpolynomial. Okay. So you see now that this is so crucial. This is why it's so crucial that you pay q in 1 over alpha. So yeah, try to prove this yourself. It's a good math exercise. But I guess you get the idea, right? Like, just because multiplicative factor is here, so you kind of pay it here. All right. And now I just need to prove to you the theorem. Like basically, we have seen the non-recursive version, which gives you this. And now instead of working with GU, we want to work with SU, with quality Q, and we want that the quality is this. Okay. So replace GU by SU here. All right. So the proof is actually quite simple. So I just copy the proof from above to here, and point out where you need to change something. Like, okay, if D is writable in G, then D is writable in H2. The proof is almost the same. That is, like, if you have some routable flow in G, if you want to route in H, just do like before. You put everything up to the root, and now you don't have GU, you have SU, right? But first of all, this projected, when you put everything up, you get the projected demand. You know before that this projected demand is routable in GU. But SU is a sparsifier of GU. So this demand itself can be routed in SU too. And that's it for this direction. So this is the easy direction. Now another direction where you can route in H, you want to route in G. Okay. So like before, you have the demand inside each part. This part is just the same, nothing changed. But how about the demand for demand between different parts? So it's like this. So let's say that F is a flow that route this demand. Fh is a flow that route the demand between different parts in H. You want to construct the flow in G. Okay. So like before, like to route thing in H. So if H actually is gonna be like this, it's gonna be like this. This is it. This is a thing, and you have some other sparsifier, not some other sparsifier SU here. So this, think of this as GU. This is like, this graph is a H when I replace SU by GU. H itself should look like this, where you have each part here, star, star. And this part is some sparsifier. So to route the flow, again, no matter what, how you route the flow in H, you need to you put everything to the root first, right? So let that thing be f of SU,